Our project is a 4-bit flash ADC using priority encoder. ADCs are useful building blocks in many applications such as data storage, read channel, and an optical receiver because they represent the interface between the real-world analog signal and the digital signal processors. In this project, an effort is made to design a 4-bit flash ADC using priority encoder. For high-speed application, flash ADCs are often used. ADC has been designed and implemented using a multi-SIM tool. Following slide shows the circuit diagram of 4-bit flash ADC using priority encoder.
Design of a 4-bit flash ADC has three important components: the resistor string, the comparator, and the priority encoder stage. We make use of 2n resistors, that is, here we need 16 resistors. The value at each tab is given by the formula as shown. We also have 2n-1 comparators, which are less immune to noise and having high common mode rejection ratio. The next stage is the priority encoder stage, which converts the encoded signal into 4-bit digital data. Coming to the working, the analog voltage is applied to non-inverting terminals of all comparators using a single line. Reference voltage, which is 1.8 volts, is applied to the inverting terminals of comparators using the voltage divider circuit. Each comparator produces digital output in the form of ones or zeros. If analog voltage is less than the reference voltage, then comparator produces logic low. Thus, all parallel comparator produces digital representation of analog voltage in the form of 0 or 1. These outputs of comparator are then applied to a fast encoder. Encoder converts those zeros and ones into binary number and produces digital binary output. This way, a 4-bit flash ADC works in order to convert the analog voltage into its equivalent digital value.
The figures shown are the expected outputs of a 4-bit ADC. The first table shows the values of the reference voltage which has been divided accordingly, where we provide 1.8 voltage as our reference voltage. The second table shows the comparator's transient response. The third table shows the transient response of output, where the first graph is the input analog voltage representation, second graph is the representation by the analog converter digital output, and the remaining four are the individual outputs of a 4-bit ADC. We use multisim to execute this project. We use 15 comparators and set 16 resistors, which is a value 1 kilo ohm. The comparators we used are the op-amp 741. And the end of the comparator's output, we have connected a yellow probe in order to indicate the outputs of the comparator. The outputs of the comparators are connected to two 8:3 priority encoders since we don't have a 16:1 priority encoder. Using two 8:3 priority encoders and 4 NAND gates and 4 NOT gates, the final output is connected to a blue probe to know the output. In this figure, we have applied 1.8 reference voltage and 1.687 as our input voltage and get as an output of 1111. It is shown by the yellow probes and blue probes are turned on.
The advantages of using flash analog to digital converter is that it is very fast compared to other types of ADCs. They are not only very accurate, but also don't require a sample and hold circuit in front of it like other ADCs. They have got comparators which are used as the sampling devices. The disadvantage of using a flash analog to digital converter is that it requires huge number of comparators compared to other types of ADCs. A typical flash converter requires 2 to the power n-1 comparators for n-bit conversion. The size and the power consumption of all these comparators make it very bulky and make it impractical for precisions much greater than 8 bits. Flash ADCs have got wide variety of applications in various sectors such as radar detection, wideband radio receivers, test equipments, and they are also found inside a delta to sigma modulation loop. Flash ADCs typically utilize a NAND flash memory where up to 3 bits are stored per cell as 8 voltage levels on floating gates.